Okay, start recording. So we are at lecture 20, I suppose. And what we were doing was uh, Garcia-Milne involution principle. And let me see. So this states that let C be C plus union C minus. C plus intersection C minus is empty. This is a disjoint union with two finite components of C, some set. So an alpha and beta be two involutions on C. So involutions mean that alpha square is equal to identity and beta square is equal to identity. This is what involution means. And let F alpha be the set of elements fixed by alpha. So alpha square, I mean, it could be that alpha applied at some x is also equal to x. And in some cases, alpha x is y, some y, and alpha of alpha y is equal to x. That is what involution means. So if this happens, this is called a fixed point. F beta is the set of elements fixed by beta.
Professor?
Yeah.
So we are saying there are two definitions of involution. That one where you get back the element, right? You apply x and then you get y, and then you apply alpha again, then you get x again, right?
Yeah, I mean, this is a special case where the first one itself is fixed. So involution means alpha square equal to identity. So it
Yeah.
can happen in two cases. This case,
Identity, you mean identity element, right?
identity means identity as a function, right?
As a function. Okay, okay.
So, so it's possible that alpha takes x to x, some x.
Mm-hmm.
Then x is a fixed point. Otherwise, alpha of x goes to y, and then if you take another alpha, then it has to come back to x.
Okay, okay.
Okay.
Thank you,
And
Professor.
we stipulate further. So further, we are saying that uh, all these um, are so. So these guys are all fixed points are all positive. Where did I write that? Well, let me just put it this way. So alpha of C minus C plus minus F alpha is contained in C minus, and alpha of C minus is contained in C plus. And beta of C plus minus F beta is contained in C minus, and beta of C minus is contained in C plus. So in particular, this means that uh, uh, these fixed points cannot be in C plus. So this implies that F alpha and F beta are all part of C plus. Because if they were part of C minus, their image would be in C plus. So, so what's happening is that you have a C which is broken into two parts, plus and minus. This is the positive part, and then you have a F alpha and a F beta. So let's say this is F alpha and this is F beta, and everything else with alpha goes to here, and everything here goes to here. So same with alpha and same with beta. So this is what is happening, and then once this happens, then the following is the thing: either a cycle of the permutation alpha beta um, contains no fixed points, or so this is exclusive, or um, it contains one point of F alpha and one point of F beta. So basically, the problem is to create a bijection between elements of F alpha and F beta, and we take the larger set and create an involution which satisfies all this part. Then one can create a bijection using this involution. So the statement is, I think the statement is fine, right, with everybody? Statement is okay. All right. So now
Professor, this also implies that if such a thing exists, then F alpha and F beta have equal cardinality.
sorry, say that again.
This also implies that F alpha and F beta have equal cardinality, right? That's what we are trying to achieve.
Yes, yes. So they have. So there's a bijection. Then bijection means equal cardinality.
Right. Thank you, Professor.
Yeah. So I mean the basic. So the history of this is we'll be shortly doing a theorem. I mean we won't be doing the theorem, but I'll be stating a theorem called Rogers-Ramanujan identities. And the history of it is that uh, they wanted a bijective proof of Rogers-Ramanujan identity, some combinatorial proof. So combinatorial proof existed, but no bijection existed. So what these guys did, Garcia and Milne did, was that uh, they showed how to create a bijection, and then they could create. They actually created the bijection using this. So they just proved that this bijection existed by means of this involution principle. So they created the involutions and then said whatever bijection follows, it follows. And so they won the prize, but it's not that they had an explicit bijection. And they had a 51-page paper, and then Doron Zeilberger and Besud, they compressed it somewhat to about 3 or 4 pages or 2 or 3 pages, but it's not so easily understood, uh, Besud stuff yet, Besud and Zeilberger stuff. Anyway, so this was the history of how the involution principle came about. Once it came about, then of course it's been applied all over the place. So it became a quite a central thing. So anyway, we are proceeding with the proof, and today I'm having a lot of trouble writing on my tablet. So the proof is as per Garcia and Milne, but explained by, again, I'm following a book by Andrews. to do that, so we construct a graph G in C. The vertices of G are all the elements of C, and each vertex we label a vertex with a plus or a minus uh, depending on whether it is in C plus or C minus. Okay, so now edges. Um, so we make edges. We label x y an alpha edge if um, if x and y are images of alpha. So I mean, x will be equal to alpha y, and y will be equal to alpha x, because alpha is a involution, right? So they are images of alpha under each other. Um, just to note that, so either I mean, you can't have, so either there is an alpha here, you know, so either x is equal to alpha y, or y equal to alpha x and y equal to alpha x, or they are not connected, or neither of this is happening. I mean, it's either connected or not. That's what it's trying to say. You can't have halfway business. So it's not a two-way star. And similarly, you have a beta. Similarly, label edges as beta edges. So there are two kinds of edges in this graph: alpha edge and beta edge. So what I'm writing.
So, Professor,
Yeah.
so either or criteria, like the either or condition for x and y being connected is because alpha and beta involutions, right? So,
Yeah, I mean, either both these things. I mean, you can't have one and the other. That's the idea.
right.
So, I mean, if there is an x here and it goes to y, right, and there are some other x1 and y1, it's not. I mean, either this is connected with alpha and this is connected with alpha, or not. I mean, that's all it's saying. So it's so
Yes, Professor.
both of them are images of each other. That's the point. So the edges are all related to uh, uh, are all given by these alpha and beta in the graph. Okay, so now we take the degree of each vertex of G is 2, and here so it has with one edge being an alpha edge and the other being a beta edge. So any x that we have, whether it's in C plus or C minus, whatever you know, uh, whatever is its image under alpha is this one, and then there could be another one which is beta. That's it. And of course,
Oh,
so degree is 2. That's the point. Only edges are basically ones which are alpha or beta edges. And this is also a degree 2. This is also considered. This is also allowed. So fixed points, for example, will have, say this is a fixed point, then this is also allowed. So this is also counted once. This is what I'm saying. So loops, I should put a different color. Loops at a point uh, contribute 1 to the degree. So actually, in graph theory, they often distinguish these two things. They call it valence. I mean, or sometimes they say loops have degree, divide by 2, and so on. As long as we know what it means, it's okay. Fine. So now the argument. So so thus we see that the cycle structure of this delta, which is alpha times beta, is given by the cycle, the connected components actually of G. So what are we saying? We are saying that you apply alpha, then you apply beta, then you apply alpha, then you apply beta, and so on. Whatever at some point it may just go just meet each other or whatever, and whatever it is that will give you a connected component of G, and vice versa, any connected component will give you the cycle structure. This is what we are saying by this. And what are the uh, you know uh, so now if a connected component does not contain a fixed point, right? If it doesn't contain a fixed point, it keeps going outward, then it looks like this. Then it is a cycle of this form. So it starts somewhere, and let's say it starts with a plus, then it will go to minus, then it goes here, then it goes again plus, because beta will take minus to plus, then this will go to minus, then this will go to plus, and this will go to something like that, and then maybe this, something like this. So the point is that pluses and minuses and alphas and betas, um, you know, are of this form. So it could, I mean, it could be that alpha starts at plus or it starts at minus, doesn't matter, but something of the other, it looks like this. So the reason is that the only points which stay in plus or minus under alpha and beta are the fixed points. I mean, even in minus, nothing stays, but the only thing which stays in plus are other fixed points. So they all have to go alternate. Okay. And otherwise, suppose a connected component has a fixed point of, say, alpha, right? Then it has to look like this. Then must look like. So it has a fixed point of alpha, so it's a plus, and then it goes out, uh, then to minus, then alpha, uh, then again beta, then alpha, and so on, right? And it has to terminate with a beta loop. Why? Because degree degree of each um, vertex is 2. So it can't cycle back here because otherwise the degree becomes 3. So it has to stop, so it looks like, you know, so somewhere here this is plus minus plus minus plus the minus the plus, and then it has to be terminated by a beta loop like this. So it has to be of this kind. Well, I made a mistake somewhere, maybe more. Well, oh wait, this is the mistake. Sorry. This is alpha. So this is beta, alpha, beta, alpha, beta, alpha, beta, alpha, and now beta. So it has to end with no wait, plus, this is minus, plus, minus, plus, minus, plus.
Yes, Professor. The loop has to be from a plus point, so
From a plus,
it has to be a beta.
yeah, because all the other alphas are coming from a minus, right? So it has to finish. So all the other, so in this, because and it has to finish with beta because all the alphas are from C minus to C plus. Listen. Okay, so that proves it. That says that if there is nothing, then it has to be like this. Then there is nothing. If there is even one fixed point, then it has to start somewhere like this and end somewhere like this. And same, I mean, same argument will go for beta. So this completes the proof. So this corresponds to a cycle which has exactly one point from f alpha and one from f beta. So this finishes the proof. I mean, we could have started with beta and ended with alpha. So in any case, this finishes. This shows. Okay. Any questions?
Oh, Professor, just a small clarification regarding when we consider that loops contribute one to the degree.
Yeah.
So when we think about when we talk about just normal graphs, in that case we consider loop to be contributing two to the degree, right?
Yeah, we have to. Yeah, so some authors mean something by the whatever they mean by the context, but that's why I said there is some concept sometimes of valence and degree. So degree often is, I mean, one of them, I don't know which one, is often talking about if you just say how many edges are incident with this vertex, then you're okay. You count this once and you count this once, right? And sometimes you say how many are coming in here and going out, like in Euler's path, then we count it twice. So depending on the context, one needs different. So I think valence is, I don't know which one is which.
Professor, I think degree is counting the number of ins and outs both, because I think we did theorems and formula which said that like summation of degree is twice the summation of edges.
Yeah, yeah. We did Euler's path, right?
Yeah.
Yeah.
Degree
So,
might be a 3, right?
yeah. But anyway, I mean, here, what I mean is this. Whatever you. So in this context, this makes more sense. That you are. So I think it's called valence too. I mean, I didn't want to increase the. So I mean, both these concepts exist. So sometimes you'd see in a paper, you'll say that this guy has actually said that what I mean is this, half the number of whatever things, or equal to number of edges incident. So in a simple graph, they mean the same thing. But in Euler's case, for example, we needed this other concept. So yeah, in this context, this makes more sense because we want to call this degree 2. And we know for sure that everything has degree 2. Otherwise, there'll always be this confusion. Right? Okay, so um, I'm going to, there are actually 2 items in the agenda. I think I'll be able to do only one of them today. So might continue after Diwali. But I want to, so in my calculus class, I don't know, Ayush, were you there in my calculus class?
Professor, I was there for the first half an hour and the last half an hour, not in the middle.
So did you see the Diwali gifts I gave to the students?
Not really, Professor. I just saw the last one.
Okay, so I gave some Diwali gifts. So I can give you one Diwali gift here. So anyway, this is it. So Andrew's approach to the Rogers Ramanujan identities. And this is Andrew's approach to discover. And these are in his number theory book. There's a classic book now taken out by Dover. It used to be very popular in India in our time. And then this was the only place where it worked. Now it's comes in. Now it's a Dover book, and it's also there in Anderson Erickson, his book with Erickson. Okay, so well, first of all, what are the Rogers Ramanujan identities? I mean, Hardy called them the most beautiful identities, and essentially, what they are these. So I'll just write down a few terms. So q raised per k square plus q sub k. So 1 minus q, 1 minus q square, q raised per 9, 1 minus q, 1 minus q square, 1 minus q cubed, plus so on. And they are equal to this infinite product, which is 1 minus q raised per 5k plus 1, and 1 minus q raised per 5k plus 4, and k going from 0 to infinity. And in our terminology, they can be written as this. This is all 1 minus q, 1 minus q square, and you divide by some things which are not there. So divide by q square, q raised per 5 infinity, q cubed, q raised per 5 infinity, and q raised per 5, q raised per 5. And then this is RR1, and RR2 is and the top part you get numbers q square 1 minus q plus q raised plus 6 1 minus q 1 minus q square and so on 9 plus 3 12, and in products you have 1 minus q raised to the power 5k plus 2 and 1 minus q raised to 5k plus 3. And again, it's helpful to know what we are writing. This is q raised to 5 infinity, q raised to 4, q raised to 5 infinity, and q raised to 5. So here, all the numbers here are 2 or 3 mod 5, and here the numbers are 1, 4, and 5, which we are deleting from all the numbers. That's how we get this, right? And the history is as follows. Okay, so in 1913, Ramanujan wrote a letter to Hardy, wrote them in a letter to Hardy. Now, you know, it's not clear. So that letter is available, but these identities don't show up there, and one page is missing. A page is missing on the letter. Okay, but later on, Hardy said that these came in his letter in January 1913, the first or second letter. It could be the second letter. Um, so nobody could prove them. So Hardy tried, he couldn't prove them. Littlewood tried, he couldn't prove them. Ramanujan couldn't prove them. And then much later, Ramanujan, when he reached uh, Britain, then he was riffling through papers in a library. So Ramanujan found them in a paper of Rogers from um, 1894. So 20 years later, basically, Ramanujan was scooped by Rogers 20 years ago, and Major McMahon, whom we've heard about, he's the guy who did the calculation. He uh, uh, he mentioned them as conjectures in his book. So his books are available. They're quite nice, actually. You can take a look. Uh, they're called Combinatory Analysis. So McMahon has an Indian connection. He was posted in India at some point. Then he went back, and then he was like a computer. He was really good, and he was interested in math. So he was hanging around, and so he mentioned them as conjectures, and then Rogers complained, wrote to him and complained, him and others, and complained that, these are not conjectures, I have proved them. And then, McMahon wrote back that, yeah, we just found out from Ramanujan and all that and so on. And both Rogers and Ramanujan published further proofs. So Rogers simplified his proof considerably and published them. So why was McMahon so excited? Because he interpreted them as partitions. So the partition interpretation. So this, uh, let me just do first guy first. Okay, so this k-square you generate using 1 plus 3 plus 5, okay, and so on. So some of the first k odd numbers, so this will give you k square. And then you stick to it a partition of less than k parts from this guy, 1 over q sub k. So this is a partition of n with parts differing by at least 2. Okay, and then you sum over all those. So this will give you this guy, one of these guys, and this side is clear. This side is, it generates partitions of n. So this is the generating. So then when you sum over this, so you sum over this. So this is the generating function of partitions of n with this, and this will give you the generating function of partitions of n with parts plus 1 and 4 mod 5. So this is easy, right? Is that clear? So this part is made up of these two components, and if you expand in powers of if you take different k's and you expand in powers of n, you will get all the partitions of n with parts differing by at least 2, and this is with less than equal to k parts, right? Uh, so this has to be at least 2 at each step, and if we look at q raised per k square plus k over q sub k. K plus 2 plus 3. This is easy as usual. This one is generating function of partitions uh, of n with parts uh, congruent to 2 or 3 mod 5. Yeah. And for this guy, what we do is we now, instead of doing 1 plus 3, we do 2 plus 4. So 2 plus 4 plus 6 up till 2k. And then you stick a partition with less than equal to k parts to this. So partition of n minus k square, and this is k square plus k. Right. So ultimately, you get generating function of partitions of n with minimal difference between parts um, at least 2 and smallest part 2. So without 1, so you have to have a 2 in there. 2 is the smallest part, and then these two. So yeah, so let's just look at it for a second. Uh, um, the first Rogers Ramanujan identity, on this side there is a difference condition. So the parts are different, differ by at least 2, and on this side there's a number theoretic condition that they're congruent to 1 and 4 mod 5. And here it's 2 or 3 mod 5, and here parts differ by 2, and there's an additional component that the minimum part is at least 2. Okay, any questions on this, on the interpretation? So here's my Diwali gift. I gave better ones to my calculus class, but anyway, this one is also nice. So this is an open problem. Prove bijectively. So some people have proposed some proofs now, but they are not very. Um, they're all somehow or the other they involve involution principle without using, I should say, without using the involution. So again, the history, if as I told you, is Garcia and Milne in 1981 gave proof of bijection, but people are not so satisfied with it because it's not like uh, thing. But it was a, it's a, I mean, it's a big open problem. If you do it, you'll become probably famous. Uh, People are, unless the answer turns out to be very easy, but which is doubtful. That will come out very easy. Okay, any questions? So, so how to discover these? So Andrews has an approach, and um, I have actually got one article on another approach by ASCII, which we won't cover. That's more analytic, but Andrew's approach is very interesting and very nice for us. So we need to understand that. So now we come back to Andrew's approach. Okay. Now what he's looking at is he's saying that if you look at, so he relooks at distinct equals odd. Let's relook at distinct equals odd. And distinct, you can look at it as that the minimal difference between parts is at least 1. And odd he looks at as a number theoretic condition, and he says um, this is uh, those items which are so the parts are congruent to 1 mod 2, right? And what he's looking for is that on this side there is, so the generating function is something of this form, right? On in both. So he's saying that let's see if we begin with something here. So begin with some type with distinct, and can we discover this capital S such that the number of partitions with S, which is the number of partitions, let's call it here, number of partitions of n with parts in S is equal to, let's call it PDN or PN, distinct parts. I mean, in our earlier notation, this was parts in S. This is better notation, but in any case. Okay, so how he does that, he lists them. So let's list them. Let's first list distinct partitions. So again, whenever it comes to listing, I find our approach a little bit easier. So we just have to add and subtract. So I'll just do that. So we are listing distinct here. For 1, it's x1. 2, it's x2. 3, it's x1 plus x2 and x3. 4, it's x1 plus x3, x4. 5 is 1 plus x4, x2 plus x3, x5, x1 more. 6, x1 plus x2 plus x3, x1 plus x5, x2 plus x4, x6. So this is 1, 1, 1, 2, 2, 3, and And then he says, okay, let's list with parts in S. So this is no problem, no part. Uh, there's only one possibility. There's one here, so I need one, right? So there's only one possibility. I have to have x1. So the question is x1 in S? Is 1 in S? Now, if parts are in S, then this is a partition. That's already there. I mean, it already makes it one part. So x2 cannot be there. So x2 cannot be in our list. So x2 is not in S. So this is saying that 1 is in S. We're saying that 2 is not in S. You get the logic? It's fine.
Professor, could you repeat that, please? The part where we say 2 is not an S.
So I'm saying that if I'm trying to see what are the parts in S, right? So we are trying to figure out S. I've listed the distinct ones. Now I start listing. I don't know whether x1 is in S, x2 is in S, so on. So I start this listing. When I start listing x1, I have to have one partition here. So x1 is there. So that's okay. But as soon as I reach 2, if x1 is this, 1 is in S, then 2x1 also is a partition, right? With parts in S, with 1 as a part. So now, since distinct has only got one partition, I cannot have x2 because otherwise it will be two of them, and here there's just one. Okay, let's do another one. If x1 is in S, then I have to have 3x1, right? x1 plus x2 doesn't count. Now I need one more part because this is just one which I'm getting. So I can have x3. So this is okay. And now I have two parts, two partitions. So these two match the distinct. Again, I keep going on. I have to have 4x1. I have to have x1 plus x3. Can I have x5? Answer is no, because otherwise I'll have three partitions. And I just have two. So I have to cancel this one.
So, Professor, I think you meant x4.
Sorry. So I can't have x4. So that means 3 is in S, but 4 is not in S. And I keep going on. So this is 5x1. Then I need 2x1 plus x3, right? Well, now I have 2 and I need one more, right? I can't have x2 plus x3 because x2 is not there, right? So yeah, x5 is contained in this list. And that makes a match. Again, let's continue. 6x1, 3x1 plus x3, x1 plus x5, right? And I can't have x2 plus x3, but I have to have x3 plus x3 because x3 belongs to S. So 2x3. I'm done with the 4, so I cannot have x6. So anyway, one can carry on this way manually, and we see that 1, 3, 5 belong to S, and 2, 4, 6 do not belong to S, and this implies that, so conjecture S is equal to 1, 3, 5, 7. Okay, so this is an approach to guess what this value of S will be. Okay, so this is guessing using Andrew's method to guess this Euler's identity. Now let's apply this to this thing. So now let's apply it for this thing. So distinct is minimum difference of parts is 1. So what about minimum difference of parts at least 2? And then again, this will give us the Rogers rounding. So let's list them. So partitions with minimum difference between parts equal to 2. So 1 is okay, x1. 2, I can't have 2x1, but I can have x2. 3, I can't have x1 plus x2 because the minimum, so I can't have this. This is not allowed. Why not? Because the minimum part is, minimum difference is 1. I need minimum at least 2. So I have x3. Then I have x1 plus x3 is allowed, right? I can't have 2x2. So I have x4 that is allowed. Right? Then I can have x1 plus x4. X2 plus x3 is not allowed because minimum difference would be 2 would be 1. Then x5 is allowed. There's 2 more. 6. There's so few that it's a good idea to do a lot more. So x1 plus x5. Then x2 plus x4 is okay. 2x3 is not okay. And x6. So 6 gave me 3. Then x1 plus x6. x1 plus x2 plus x4 is not allowed, but x2 plus x5 is there. x3 plus x4 is not there. And we have x7. So 7 has 3. Let's try this. X1 plus x7. X2 plus x6. x3 plus x5. And x8. So 1 more. X1 plus x3 plus x5. x1 plus x8. x2 plus x7. x3 plus x6. x4 plus x5 is not allowed, and x9. So 1, 2, 3, 4, 5. Okay, so this is 1, 2, 2, 3, 3, 4, 5. Okay, so now I want to find S over here. This is no problem. X1 is no problem. Right now, here I can have 2x1, and that's it. So x2 is not there. So x2 is not there. because it's just 1. And again, I have 3x1, so x3 is not there. So I just note down here that 1 belongs to S, 2 does not belong to S, 3 does not belong to S. Then I have 4x1 from this guy, and I need 2, so x4. So 4 belongs to S. Is this clear what I'm doing?
Yes, Professor.
Okay, so 5x1, x1 plus x4, x5 can't be there because we are done with 2. So x5 is not there. Okay, 6x1, 2x1 plus x4. See, why am I not putting x2 plus x4? Because x2 is not there. So I can't do x2 plus x4. But I do need a 6 now because there are 3 here. So 6 belongs to S. 7x1, 3x1 plus x4, x1 plus x6. Okay, that's it. That means x7 is not there. Again, x2 plus, there is nothing here. I can't do. x3 plus, I can't do because x3 is not there. 8x1, 4x1 plus x4, 2x1 plus x6, x2 plus x6 I can't get, x3 plus this, but I can get 2x4. And again, that means that I don't get 8. All these 4 are done. Then we have 9x1, 5x1 plus x4, 3x1 plus x6, x1 plus 2x4, and let's see, x2 can't do, x3 can't do, x4 is already covered. So I do need a x9. So I mean, you can keep going on, and what we get is that only 1, 4, 6, 9 belong to S. So guess is S is equal to 5k plus 1 and 5k plus 4 mod 5. Let's write it like this. Belong to S. Okay, so that is Andrew's approach for discovery of first RR, and I'll give you a couple more maybe in the assignment to try. Okay, any questions on this? Any questions on this approach? Okay, there's one more thing I can just add here. There's another approach. Uh, I'm not giving the complete approach, but this is covered in, there's a paper I have on in resonance, how to discover the Rogers-Ramanujan identities by me. It's available on my website. Um, so here, this is ASCII's approach. But the method that I'm going to talk about is there's a Euler's algorithm for if you have a sum, how to guess the product. . This is a bona fide algorithm. People use it, so they get a lot of sums, and then they apply this algorithm on the computer to guess the product side. So we'll try it on this guy. We'll try it on the second Rogers Ramanujan identity. I'll show you that.
Professor,
Yeah.
when we say guess the product, do we mean guess it accurately or approximately?
Guess it what?
When we say if you have a sum, how to guess the product, do we mean that approximate the product or like guess what the actual product will be?
Yeah. So yeah, we want to guess what the actual product is, if there is a product. So there is an algorithm due to Euler, which I'll just explain to you the basic idea. So we'll apply it to this guy. I mean, basically uh, everything I like. It seems to be that it is linked to Euler somehow. Euler as a uh, Euler is really good. So they say that Euler's. I don't know who. ASCII said that we could use Euler's textbook to teach calculus. Only the students are not so good. That's the only problem. But we should, if we do it, then we'll probably it's very modern and very clever ways of doing things. So Euler wrote a book on calculus, right? Analysis of the infinite or something like that. So if we can just translate it from Latin and use that, it might be a good idea. It's full of clever tricks, which are in some form or the other they are used these days. So it's not that you'll see an algorithm which is very complicated in a paper, but essentially it is Euler's. It's this algorithm. To try it out, you'll realize, oh, this is what they do. So now it's implemented in various packages. Anyway, so let me show you this. So let's just write a few terms. So the right hand side is of the form, if you expand all the 1 over 1 minus q into series, then it's of the form 1 plus q square plus more terms, right? Is that clear? So the smallest term will be q square, because 1 over 1 plus q, 1 minus q will become 1 plus q square, so on. And this will have the smallest term, q raised per 6. This will have the, whatever you get by expanding these guys, you will get q raised per 6 as the smallest, right? So this is q square is the smallest term. So how do we delete a q square? You multiply by 1 minus q square. So you get 1 minus q square plus q square times 1 minus q square, and this q square might delete itself. So what we do is we do this. So let's do it on this guy, and we get 1 minus q square plus q square, and now you have 1 minus q square over 1 minus q, so it's 1 plus q plus q raised per 6. You multiply by 1 minus q square, you get just this guy, plus q raised per 12, and you multiplied by 1 minus q, you get 1 minus q, 1 minus q cubed. So, is that okay? So the first few terms, I just have 1 minus q square plus q square plus q cubed plus q raised per 6 over 1 minus q plus so on. So this gets cancelled. And this is of the form 1 plus q cubed plus 12. Is that fine?
Professor, could you go over the first step of how we got the form?
So
Are we just expanding the whole sum?
So it's 1 plus q square over 1 minus q. So if I take 1 over 1 minus q and write it as 1 plus, so uh, uh, if I take from here this part, if I take 1 over 1 minus q and write it as 1 plus q square and then multiply it, I'll just get 1 plus q square plus q cubed and so on.
Right.
And similarly here, I can do 1 over 1 minus q, and whatever I get, I'll get q raised per 6 as the minimum.
Okay,
And
so we're expanding the whole sum. It's not a power series of any sort.
yeah, I mean, it's like a formal power series. You just expand it. If you expand it, you'll get 1 plus q square plus something. I don't know what, but you'll get that.
Okay, yeah, thank
And
you.
then the trick is to multiply by 1 minus q square. And then when you do that, this first q square will go away. So you'll get 1 plus something bigger. And this something we can see is q cubed. So now let me multiply by 1 minus q cubed. So I multiply by 1 minus q cubed over this one. So I get 1 minus q cubed plus q cubed times 1 minus q cubed plus q raised per 6 times 1 plus q square uh, plus q raised per 12 over 1 minus q plus there are more terms. And now I get this q square gets q cube gets cancelled. Q raised per 6 gets cancelled. Yeah, so this gets cancelled. This also gets cancelled. So it's of the form 1 plus q raised per 7 plus something. Yeah, is that clear? Is that clear? Please say yes or no.
So, Professor, it's in some way like removing the denominator from all the terms. And we go step by step.
Yes. But are you clear that you're getting 1 plus q raised per 7 plus some higher term?
Professor, I am still kind of calculating. So can I get a half a minute, please?
So have you got this 1 minus q cubed plus q cubed over here times 1 minus q cubed plus q raised per 6 times 1 minus q cubed is 1 plus q square and so on.
Yes, Professor. Professor, I got it. This
And
is
then I just cancel whatever and I get q raised per. I mean, this is what comes up. I mean, it's not, I'm just guessing what it is, right? I'm just multiplying and seeing what comes up. Anyway, so what do I multiply with next? What do you think I should multiply with next?
1 minus to the 7.
So I multiply by q raised per 7 and then I get rid of 1 minus q raised per 7 plus q raised per 7. I mean, calculations keep getting more and more complicated, um, but this is what I do, okay? And if I keep doing this, then I will eventually get, I mean, I do it many more times and I notice a pattern until I get a pattern. And I hope that at the end I get no power of q, I get 1. So we hope that, or we conjecture that if we keep doing it forever, we'll get 1. And then the answer will be S will be 1 over this guy. Okay, so that's the algorithm. You keep deleting one after the other and get it. So as an aside, let S be, why am I calling it Euler's method? Do you know what this function is called? So suppose I want to get rid of 1 over 2 raised per s. What do I multiply with? Right? So I'll multiply by 1 minus 2 raised per s, the first term, then I'll have minus 4 raised per s plus 3 raised per s minus 6 raised per s, so on. What do I get? I get all the terms which have which are divisible by 2 will cancel. Like this term will cancel this guy. So I'll get 3 raised per s minus 1 plus 3 raised per s plus 1 over 5 raised per s plus 1 over 7 raised per s. Okay, anything which is divisible by 2 will cancel. Now if I multiply by 3 raised per s, 1 minus 3 raised per s, then everything that is divisible by 3, so in particular this guy will cancel, right? Because I'm multiplying by 1 minus 3 raised per s over here. So in this term, I'll get 1 over minus 1 over 9 raised per s. So this will get cancelled. 10 is already gone. I'll get 11 raised per s. 12 is gone. 13 raised per s and so on. And so on. So what do you think s is? So product 1 over 1 minus 1 over 3 raised. So this is Euler's product for zeta function. Okay, informal, I would say, informal derivation. It's not a proof. Okay, so yeah, I think we've run out of time, which is good because I've run out of things to say. So next time we will uh, finish partitions. I need actually, um, I needed a longish theorem which I didn't do earlier, but I need that for the this thing. I want to prove this. But to prove it, I need to do one additional uh, step in the previous calculations. Okay, any questions?